In this lesson, we'll talk about infinite sequences and we'll introduce summation notation. An infinite sequence is any function with the domain of natural numbers. For example, a function defined like this. This really represents odd numbers because for every natural n, we are doubling it, which gives us even number, and then subtracting 1, which gives us odd number. So let's see how this function really looks like. The input is 1, 2, 3, 4, 5, and so on. So in this row we'll have our n, and then for every n we assign a value. The value will be called a of n. That's a value of function a at the point n. If you plug it in 1 in this expression, 2 times 1 minus 1 is 1. So the input 1 will result in the output 1 as well. The input 2 will result in the output, well, 4 minus 1 is 3. The input 3 will result in the output 3 times 2 is 6 minus 1, so it's 5, and so on. The input 4 will give us the value 7, and input 5, 9. So we see how this sequence is produced. It's a sequence of odd numbers, and here we have a general rule that tells us what to do, how to find the value for the nth entry in the sequence. And those numbers listed in the sequence are called terms of the sequence. Notice that because the domain of the sequence is all natural numbers, the order of the numbers in a sequence is actually important, in opposed to a set, where we can list the numbers in any order and produce the same set. So sequence, order is important, sets, order is not important. Okay, so if our domain is all natural numbers, we'll produce an infinite sequence, because such sequence has infinitely many terms. Well, we can also talk about finite sequence. That's just enough to take for a domain the first finite number of elements from natural numbers. So if the domain of a sequence is from 1 to n, when n is a natural number, such a sequence is called finite. Okay, we mentioned that sequences are really functions. However, because of the nature of domain, which are natural numbers, we are looking at those functions by listing the values of consecutive terms of the sequence. So because quite often we are going to look at many terms at once, it is customary to denote the value of a sequence A at the point n as A with subindex n rather than A of n. And also, to indicate the whole infinite sequence, we may want to use notation an in the braces. So the braces here are very similar to the set notation, however they carry a little bit more information because this doesn't only indicate the values of the function a, but those values are ordered. So if we write an in the braces, that denotes the whole sequence. That means, for example, infinitely many terms, in opposed to listing just an, which represents only nth term. So we can write our sequence in the following way. a1, a2, the terms are disjoint by commas. a3, a4, a5, and then 3 dots, indicating and so on and so on. And if we have general term, it's a good idea to indicate this general term an. And then again 3 dots, indicating that we are going towards infinity, following the same pattern. Let's see one example. A sequence an with general term an defined as 2 to the n, we can see as the list of terms. For example, if n is 1, then the first term is 2. So this is like 2 to the 1. If n is 2, then the term is 4. If n is 3, then the term is 8. N is 4, term is 16. N is 5, our term is 32. That's good enough to see the pattern. And then 3 dots telling us and so on. And then we'll list the general term 2 to the n, and so on. So that's a sequence of powers of 2. Sometimes we'll deal with alternating sequences. What are there? Well, those are sequences that will alter the sign from term to term. So the first term is positive, the next negative, and positive and negative, and so on and so on. For example, we can have alternating harmonic sequence. That's the name of this specific sequence defined by the general term -1 to n plus 1 times 1 over n. 1 over n without changing signs is called just harmonic sequence. But if we start changing signs every term, then we have alternating harmonic sequence. Let's list the first couple terms of this sequence. a1, we plug it in 1 for n, then our exponent is 2, so -1 to 2 is positive. Okay, so we start with positive term first, and then 1 over 1 is just 1. So the first term a1 is just 1. Second term a2. Well, we'll plug it in 2 here, so the exponent is 3. So -1 to the odd exponent is negative, and then it's 1 over 2, -1/2. The following term a3. If I plug it in 3 for n, then it's -1 to the 4 to the even exponent. It makes it positive, and it's 1 over 3. So as you see, the sign changes from positive to positive, and the next one will be obviously negative, because the parity of the exponent changes, and the sign really depends on the parity of the exponent of -1. So it's negative, and since n is 4, it's just 1/4. And we know that the next one will be 1/5, and the following one -1/6, and so on and so on. So that's alternating harmonic sequence. The other interesting types of sequences are recursively defined sequences. What are they? Well, maybe we can't really give the nth term explicitly like we did before, but the nth term is defined through the previous terms. For example, a Fibonacci sequence. If we start with first two terms being 1, so the first term is 1, second is 1, and the third term, well, it's not defined here, but for n bigger equal 3, that means particularly for 3, I need to follow this recipe. That's the recursive formula. Why is it recursive? Because the nth term is defined through the previous terms. We have to know the previous ones in order to figure out the next one. So particularly for n equals 3, this will be a3, but that's 3 minus 1, so it's really a2, and this is 3 minus 2, so it's really a1. Oh, but we know what's a2 and a1. Those are our previously defined terms. So it's just 1 plus 1, making it 2. And the following term we recover by saying, okay, a4 is the same as a3 plus a2. So you see what's happening. To get the next term, we're adding the two previous ones. So a4 is a3 plus a2, so it's 3. And the following one will be a4 plus a3, so it's 3 plus 2, so it's 5. And the next one, add the previous two terms. 8. 8 plus 5, 13. 13 plus 8, 21. And so on. So that's how we create Fibonacci sequence. This is the standard one, starting from two ones, but we could actually start from any two numbers as long as we follow this recipe. To get the next term, add the two previous terms. Such sequences are called Fibonacci sequences. In this exercise, we're asked to list first 5 terms of the following sequences. This is not too difficult exercise. I really wish that you try on your own before you see me doing it on the video, but you can watch the first example. So what's a1? a1 is, we plug it in 1 for n, so it's really 3 plus 2, so it's 5. a2, well, we plug it in 2 for n, so 2 times 3 is 6 plus 2 is 8. a3, 3 times 3, 9 plus 2 is 11. And two more terms. If n is 4, maybe I don't need to write a1, a2, a3 anymore. It's just the outcomes, just the values of the terms. So for a4, we'll have 4 times 3, 12 plus 2 is 14. And finally a5, 15 plus 2, 17. So 5, 8, 11, 14, 17. Such a sequence is called arithmetic sequence. You can probably notice that what's happening between terms is we're adding 3. So 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 3 is 17. So a sequence with the difference between consecutive terms being constantly the same is called arithmetic sequence. And we'll talk about arithmetic sequences more in depth in the next lesson. The next example, this is an example for another alternating sequence. So the sign will change. The sign is hidden in this power of -1. Okay, so if n is 1, we have a negative sign, and we have 1 over 2, so we have -1/2. If n is 2, then the sign becomes positive, and we have 2 over 3, so it's 2/3, positive 2/3. If n is 3, again we have a negative sign, and it's 3 over 4, -3/4. So you see what's happening, the numerator is increasing by 1, and the denominator is increasing by 1, and we are changing signs. So what will be the next one? 4/5. And the last one, -5/6. Let's see the following sequence. If n is 1, we have 1/2 times 80, which is 40. n is 2, that will be 1/4 times 80, which is 20. n is 3, that will be 1/8 times 80, giving us 10. n is 4, 1/16 times 80, or rather 1/2 of whatever it was before, because if the power increases by 1, we basically multiply the previous value by 1/2, so it will be 5. And the last one, whatever it was before times 1/2, it will be 5/2. Notice that in this case, what we really have done, it was division by 2. So the first term divided by 2 is 20, then divide by 2 is 10, divide by 2 is 5, divide by 2 is 5/2. So any sequence such that the quotient between consecutive terms is constantly the same is called a geometric sequence. And again, we'll talk about geometric sequences in the following lectures. And finally, interesting example, this general nth term of a sequence is defined as n factorial. Well, what this factorial stands for? Factorial is a shorter notation of multiplication. N factorial really means the product of all consecutive numbers from 1 until n, with the additional rule that 0 factorial is defined to be 1. This factorial notation is really powerful. You can see that this grows really quickly when n goes a little bit up. So the first couple numbers is okay to calculate by ourselves, but if n is, for example, larger than 5, I would suggest that you use a calculator. On the graphing calculator, factorial can be found under Math, then scroll till Probability, and number 4 is Factorial. So let's go back. If we would like to find out, for example, 5 factorial, we go Math, Probability, number 4. And we have factorial. Enter. It is 120. Okay, let's list the first 5 terms of the sequence. 1 factorial is just 1. 2 factorials means 1 times 2, so it's 2. 3 factorials, it's 1 times 2 times 3, so it's 6. 4 factorial is 1 times 2 times 3 times 4, so it's like 6 times 4. Oh, it's 24. And the last one, 5 factorial, if this is 24, we still need to multiply it by 5. That turns out to be 120. You see the numbers are growing really fast, but we've been asked only for the first 5 terms. In this exercise, we're asked to find particular terms A8 and A15 for the sequence given by this general term. So what we do is just plug it in n equals 8, so A8 equals -1 to the 8, it's positive because we have even exponent. 8 minus 1 is 7, and 8 plus 1 is 9. So A8 is just 7/9, not a problem here. A15, again we plug it in 15 for n, so -1 to the 15 is negative. 15 minus 1 is 14, and 15 plus 1 is 16. So -14/16. We could simplify this to -7/8. Okay, this time we want to find A4. So we're looking for A4. If we know that A1 is 2, and the general term is given recursively, it's some expression that involves the previous term. Well, because A4 is not very far from the start, let's list the terms until we'll hit A4. So A1 is 2. A2, by using this formula, would be 2 minus 1 is just 1 times A1. But A1 is 2, so it's 1 times 2. Therefore, A2 is also 2. A3, well, A3 is 3 minus 1 is 2 times A2. So it's 2 times the previous term, which was 2. Okay, it's 4. So we have 2, 2, 4. And finally, A4 will be the same as 4 minus 1, which is 3, times the previous one, A3. But A3 is 4. So we've got 12. Therefore, our A4 is 12. Final answer. In this example, we would like to simplify expressions involving factorials. We can do it by hand. For example, n-1 factorial is a product of consecutive natural numbers starting from 1 and ending on n-1. And n factorial is a product of all the numbers from 1 till n. Therefore, the previous number is still n-1 and then times n. Now you can see that we can reduce all common factors. That means all the numbers until n-1, because all of them are the same, except that we are left over with the extra n here. So the expression after simplifying is simply 1 over n. Okay, let's simplify this expression. 50 factorial is 1 times 2 times 3 times until we'll get 48 and 49 and 50. Why did I list so far until 48? Well, because I predict that we can cancel all the numbers until 48 because of this 48 factorial in the bottom. So 48 factorial is 1 times 2 times 3 times 48. And 2 factorial is 1 times 2. So now we can cancel all those numbers from 1 to 48. That means 48 factorial could be reduced even like this, and then just write in the top that what's left is 49 and 50 in the numerator. But we can still reduce with the 2. For example, 2 with 50 is 25. So overall we have 49 times 25, which after multiplying gives us 1225. So it's a good idea to be aware how the factorial notation works and how can we simplify. It is useful to simplify by hand if some of those numbers are very close to each other. But if, for example, this will be 24 and that's 16 or something, that will be really hard to figure out what's the final answer. And in such cases, we need to use calculator. And now I will show you how to simplify this expression using graphing calculator. If we would like to evaluate 50 factorial, that's how we do it. Probability, number 4, and then divide by open the bracket, 48 factorial, so again math, probability number 4, times 2 factorial. Well, we know that 2 factorial is just 2, but if we wish to enter as it is, then let's do it again. Number 4, bracket, and enter. So the value is 1225 as we calculated by hand. Next, if we see a sequence, we would like to analyze what is the governing pattern for these numbers and possibly find the general term of such sequence. Okay, if we observe the first sequence, we can notice that all these numbers are multiples of 3. Even more, those are actually powers of 3. So let's list them. 1 can be seen as 3 to the 0, 3 as 3 to the 1, 9 as 3 square, 27 as 3 to the 3, and 81 as 3 to the 4. Okay, so the general term, the nth term, should be 3 to something. What is this something? Well, let's observe. That was second term, and we had 3 to the 1. That was third term, and we've got 3 to the 2. So the exponent seems to be 1 lower than the index of the term. Okay, therefore this should be 3 to the n minus 1. So our final answer is an equals 3 to the n minus 1. So when creating this formula, we look for certain regularities, observe the pattern, we may guess some expression, and then in the end it's a good idea to check if what we've done is actually working. So why don't we check? If n is 1, then it's 3 to the 1 minus 1, 3 to the 0, yes, it's 1. If n is 2, then it's 3 to the 1, yes, it's 3. If n is 3, 3 to the 2, yes, it's 9, so yes, that definitely works. In the next sequence, we can observe what's going on from one number to the other number. Is that the same regularity or not? Well, it looks like we're adding 5 all the time. 7 plus 5 is 12, 12 plus 5 is 17, and so on. We are adding 5 all the time. So, the first term I could see as, for example, 2 plus 5. The second term I could see as 2 plus 2 times 5. The third term I could see as 2 plus 3 times 5, 2 plus 15, and so on. Well, let's try to guess a formula for nth term. It should be following this pattern: 2 plus certain number of 5s, so something times 5, or 5 times something. Well, what would this something be? Here the something is just 1, over there is 2, 3, so the something really corresponds to the index of the term. That was first term 1, second term 2, third term 3. Therefore we can guess that the nth term will be 5 times n. And then we can check just by plugging in a couple n's and see if it works. For example, fourth term, a4, according to our formula, will be 2 plus 5 times 4, which is 22. So it confirms. So this formula really works for the general term. And the last example, we see that the sign alternates. Therefore, in our general term, we have to have -1 to some exponent. What would this exponent be? We need to check parity. The first term is negative. So if I put n and n is 1, this will give me negative, so that works. Now, I see a fraction. So let's put a fraction here. And the numerator of this fraction is constantly 1. However, the denominator, there is some pattern here. Those are perfect squares. So here we have 1 square, over there 2 square, 3 square, 4 square, and so on. And the number that we square corresponds to the index of the term. So overall the pattern should be n square. That's my guess. Let's check it. For example, this term is the fifth term, so a5 would be -1 to the 5 is -1 over 5 squared, which is 25. Yes, it works. So that should be fine. This is our answer for the general term. Here we have some application problem. A car loses 20% of its value each year. If a new car costs $24,000, what is its value after 4 years? Give a formula for the value of this car after n years. Well, let's answer the first question first. So, the new car costs $24,000. After 1 year, the value of the car loses 20%. So the remaining value is actually 80% of the original value. Therefore, we calculate as 80%, which is 0.8 times $24,000. In this type of questions, I would suggest that you don't multiply these numbers. We'll observe the pattern first, unless we actually need to find out the particular value. So, what's happened after second year? So, 2 years after. Well, we have the value of the car being 80% of the previous year. So it's 0.8 times 0.8 times 24,000. The more efficient way of recording this would be 0.8 square times 24,000. Okay, let's do the same for the third year. Again, 80% of the previous value, so we need to multiply the previous value by another 0.8. So we'll end up with 0.8 cube times 24,000. And finally, after the fourth year, we'll have 0.8 to the 4 times 24,000. So what is its value after 4 years? Well, now we can use calculator and we can evaluate this to 9,830.40. So the value is $9,830.40 after 4 years of using this car. And now the second question, give a formula for the value of this car after nth year. Well, let's observe the pattern. After second year, we squared the factor 0.8. Third year, we cubed. Fourth year, we raised to the 4. Therefore, the general formula for a nth term would be 0.8 to the n times $24,000. So using this formula, we can find out the value of the car, let's say, after 10 years or 15 years. We don't have to list the terms of the sequence. We can just jump to the particular term at once. So this formula gives us value of the car after nth year. Next, we are going to talk about series. Series are really built on sequences. The word series is actually singular and plural, so there's no difference between one series or many series. What is it? Well, basically this is a sum of all terms of a sequence. And since sequences may have many terms, sometimes infinitely many, that causes some trouble how to summarize them and how to record such sum, because, well, if we want to summarize 100 or 200 terms, it's kind of annoying to write down every single term with pluses between. So what we do, we use a special sign, sigma sign, that will tell us that whatever comes after the sigma sign will have to be summarized. We'll see in a second how this works. So a series is a sum of the terms of a given sequence. So if the sequence is infinite, the series will have infinitely many terms. Those entries are also called terms for series, and such series will be called infinite series. If we have finite number of terms, then it will be a finite series. We can add just the first few terms. In this example, only 4 terms. How do we know that this is infinite? Well, because of these 3 dots. It goes towards infinity. And sometimes we may be interested in summarize only a certain number of terms, creating partial sums. So those partial sums will be denoted as with subindex n, where n will tell us how many terms we're going to summarize. So in this case, this is a partial sum of the first three terms, S3, using the same example of the infinite series. Now let's try to understand how the summation notation works. This big sign is called sigma, and after sigma we're going to write certain expression, but this expression will depend on a counter, because we need to count which term we're adding. So this counter could be called I or K or even sometimes N. However, N is usually reserved for the last index, so we usually use I or K, but it could be any other letter. Now at the bottom of the sigma and at the top of the sigma, we'll list the limits. These numbers will tell us which terms of the sequence with the general term I we should actually add. So here we are adding all terms from 1 to 5. So since this is just I, if I is 1, then we write just 1. If I is 2, then we write 2. I3 gives us 3, I4 gives us 4, I5 gives us 5, and that's the last term that we add, because that's the upper limit. So this number will be called upper limit. And the bottom number will be called lower limit. While I by itself can be called a counter or index of summation. So that was example of finite summation. We had only 5 terms. Here we also have a finite summation, but the number of terms really depends on this n that is taken for the upper limit. So if the n is just 2, it will be only 2 terms, but if n is 100, it will be 100 terms. So here we have a sum of I from 1 to n. That means all natural numbers from 1 to n. And they can be written like this with the 3 dot in between, because we really don't know what the n is. Or finally, the upper limit could be infinity. Then we have infinite series. As you notice, we still have the same expression, but now we have infinitely many terms. So this summation really means that you add 1 and 2 and 3 and the general term. So this could be indicated here or not. It depends if we have this formula or not. And then 3 dots after to indicate we're going towards infinity. Let's analyze properties of summation notation. What do we have here? Well, we summarize an expression that is called C, and this C has nothing to do with I, which means that every single term is a constant C. C in this case will stand for constant, but it could be a number, 5 or any other letter, as long as this letter is not the same as the counter index. Then what the sum really stands for is C plus C plus C plus many C's until we'll count n of them. So that's the last nth term. So there's n times the same constant C, which can be written as just n times C. That's why the sum of n terms constantly being C is just equal n times C. Particularly if I have a sum from I equal 1 to 10 of a number, let's say 8, that will be 10 times 8, which is 80. However, if this 10 is not specified here, if I have just sum from I equals 1 to n of 8, that will be 8 times n, an expression that means the same as this sigma notation. The second property, this is sum of consecutive numbers from 1 to n. As you remember, the sigma of I really means 1 plus 2 plus 3 plus until we'll get n, so n first consecutive natural numbers. To add these numbers, we actually have a formula, and that's a formula that gives us the overall sum. Let's see how come. Well, if I call this sum, for example, S, and I will write this S again underneath, but the other way around, starting from 1 and adding this way. So the one before last will be n minus 1 and then plus n. Then when we add these two equations, I will have 2s on one side, but then over here I could add column by column, and it will happen that each column will have a sum n plus 1. So we have n plus 1 from this column, and n plus 1 from that column, and so on until the last column, which is still n plus 1. So that means that 2s is equal, well, how many of those n plus 1s? The same many as many columns, but we had n columns. So we have n times n plus 1. And then when we solve for s, it's simply to divide by 2. So we have n times n plus 1 divided by 2. And that's a formula for any sum of consecutive numbers from 1 to n. So let's highlight this formula. That will be quite important. It's a good idea to memorize. What we really do, we take the last number, multiply by the next, n plus 1, and divide by 2. So in practice, if I have a sum with I from 1 to, let's say, 100 of I, that really means last number n, 100, times 101, divide by 2. So it's really 50 times 101. Oh, that's nice. We don't even have to use calculator. It's 5050, 5050, and no effort whatsoever. Imagine how long you will have to add all the numbers from 1 to 100, doing one by one, even if you use calculator. So this is very useful formula. Please memorize it. And another property, now we have a summation of constant times some term ai. Well, this property tells us that we can always pull the constant out of the summation, because constant doesn't depend on the index I. So the sigma really tells us we have c times a1 plus c times a2 plus c times an finally. Then we can pull the c out as a common factor, and then we have some a1 plus a2 plus until an. So any constant can be taken out of the summation notation. And finally, if we have a summation of either sum or difference of two terms, like two sequences for example, then we can split this summation over the addition or subtraction, so rewrite it that way. Well, for example, if I have something specific, well, if n is, for example, 2, then we'll have a1 plus b1, that's first term from the left-hand side, and let's say we have another term, a2 plus b2. Obviously, this could be regrouped by putting together a's first, and then b's as second ones. So that's the property. You can rearrange your terms. Therefore, you can split the summation over addition or subtraction. Okay, using the above properties, let's try to find sums of the following series. Here I have a summation of the difference of two things. So I can split this over sigma of I square from 1 to 5 minus sigma of 1 from 1 to 5. Since I don't have a formula for I square, but we have only 5 terms, so we can actually list them. I square when I is 1 is 1 square, which is 1, plus when I is 2 is 2 square, and then I3 means 3 square, I4 gives us 4 square, and I5 gives us 5 square. So that's the first sum. We actually need to perform this summation. However, the second one, using the property from previous slide, we can just say it's 5 times 1, because we have 5 terms, each of them is 1. Okay, so what do we have here? 1 plus 4 plus 9 plus 16 plus 25 and minus 5. Okay, so 4 plus 1 gives us 5, subtract with this 5, and 16 and 9 is 25 plus another 25. That really gives us 50. That wasn't too painful. Well, the next one is alternating series, and since signs for each term differ, however there's not too many terms, maybe let's just list those terms. So if k is 2, this becomes positive, and then it's 2 times 3 is 6 minus 2 is 4 for the first term. If k is 3, then we have a minus, and then is 9 minus 2 is 7. If k is 4, then we have a plus again, and then it's 12 minus 2, which is 10. If k is 5, then negative to the 5 is negative. 5 times 3 is 15 minus 2 is 13. And finally, when k is 6, then we have positive again. 6 times 3, 18 minus 2 is 16. So that's k6, k5, k4, and so on. k3 and k2. Notice we didn't start from 1, we started from 2, because the lower limit is 2. And then just add them. So we can add all positive numbers first. 16 and 4 is 20 and 10 is 30. And then all negative numbers after. So minus 7 and 13 is 20. Altogether 10. In the next example, we can use some of the properties. For example, we can split this summation over the addition. So we can rewrite the sum as sigma from I equals 1 to n of 2 plus, and then it will be sigma of 3i from I equals 1 to n again. However, this 3 as a constant can be taken out of the sigma, and also sigma of 2 can be calculated. We have n terms, each of them is 2, so it's 2 times n. Then we can pull the 3 as a common factor out of the sigma notation, and we end up with something that we know the formula for. It's a sum of consecutive numbers from 1 to n. So we have 2n and then plus 3 times this sum from the previous slide is n times n plus 1 over 2. So we already have the final expression. We could put this final expression under the same common denominator, for example under 2. That will become 4n, and this one is 3n, then let's multiply through the bracket, so it's 3n squared, and then it's 3n plus 3n. Okay, that means that we really have 3n squared plus 7n, and we could pull the n out of the bracket as a common factor, so it will be 3n plus 7 over 2 as a final nice answer. And the last example, again, we can split this summation over the subtraction, and at the same time we can pull the 1/2 as a common factor out of the sigma. So it will be 1/2 sigma of n when n changes from 1 to 20. So you see, this time instead of I we have n, but that's still a counter that changes from 1 to 20. And then minus sigma of just 1, again from n equals 1 to 20, but 1 doesn't depend on n anymore. So it's 1/2, and here we have a sum of consecutive numbers from 1 to 20. So according to our rule, that will be the last number, 20, times the next 21 over 2. And then it's minus 20 terms by 1, so it's just 20. We could reduce the 2 2's, making it 4 with 20, making it 5. And then we have 5 times 21, 105, minus 20, leaving us with 85 as a final answer. Finally, we have some series written explicitly, and we want to rewrite them using summation notation. So let's observe the pattern. What do we have here? Those are perfect squares. That's a perfect square of 4, 5, 6, 7, and 8. Okay, so I could, for example, write that we summarize I square because it's something square, but the something changes from 4 to 8. Well, let's record this. I changes from 4 to 8. And now this sum really represents our series. Okay, let's look at the second example. Here the sign alters, so we should have some factor -1 to something. We need to figure out if this something will be the counter or change the parity of the counter. We'll see in a second. So sigma -1 to something. And then what's the pattern? Well, those are consecutive numbers starting from 6 ending on 10. So if I will just write I, and then I will start from 6 to 10, that will cover for the numbers. But let's look at the sign. If I would put I as an exponent here, then if I is 6, that will be even. Oh, that works, because -1 to the even exponent gives us positive term, and the first term is positive. And -1 to the 7 will give us negative, so that's good. So this formula should work. And the last one, again, the summation notation. Let's observe the pattern. It is 1/3 to certain power. Or we could say 3 to the negative power. For example, 3 to the -2. That's 3 to the -1. That's 3 to the -3. Also, we need to accommodate for the changing sign, so it will be some -1 to something. Okay, the base is known for sure, it's 3. And then it's negative exponent. What kind of exponent? Well, we start with 1, and then 2, and then 3, and then 4 until infinity. Oh, that means the upper limit would be infinity. And let's call it I. So I would change from 1 to infinity. That's great. Let's accommodate for sign. I need to start with a positive. However, if I put I here, then it will make it negative. So I need to change the parity of I. So let's write I plus 1 here. We can just move this 3 to the -I a little bit farther because it's too squishy. Times 3 to the -I. And it looks like this formula works perfectly fine for our series.